Hello and welcome to Algebra 2, Lesson 69. In this lesson, we're going to learn about exponential functions. So an exponential function is of the form, we see here that we have f of x is equal to a, which is our base, raised to the power of x. So what makes this a little bit different for us is that we've never seen a variable involved in the exponent before. So what we'll do here is we'll define a to be any number that is larger than 0, and it's not allowed to be equal to 1. The reason we put these restrictions on the base is so that we can say that x is any real number. And you can just think about for a moment why you need those restrictions on a to make this all work out. Let's say a was allowed to be some negative value. Just to make it simple, let's say it's -2. So if I had -2 as my base, and I raised it to, I don't know, let's say the number 3. You'd say, okay, there's no problems there. -2 cubed, or -2 to the third power, is -2 times -2 times -2, which we know would be -8. So that's all fine. But what if we said I want -2 raised to the power of 1/2, or 1/4, or something like that? Well, then this is equal to the square root of -2. And although we can deal with this using the complex number system, the answer is not real, right? So if we're dealing with just real numbers only, we want to restrict a to, again, be greater than 0, and it's not allowed to be equal to 1. Now, let's talk about why it can't be 0. If you think about having 0 as your base, if I raise 0 to some positive value, let's say I square it, 0 squared we know is just 0, so that's all fine. But I can't raise 0 to the power of 0, that's undefined, and I can't raise 0 to a negative value, because if I did something like 0 to the power of -2, we know this is 1 over 0 squared, and this is 1 over 0, which is undefined. Undefined. So that's why we have these restrictions. Now, let's cover this last one here where we say a does not equal 1. Why do you think a, the base, is not allowed to be equal to 1? Well, we would no longer have an exponential function. We would have a linear function. You might say, well, why is that the case? Well, if I say f of x, to make this really simple, instead of f of x, let's just say this is y is equal to a, I'm just going to replace that with 1, raised to the power of x. So just think about some ordered pairs. Let's just do 2. Let's say I picked 2 for x. What would y be? 1 squared is 1, so y would be 1. Let's say I picked, 10 for x. 1 to the 10th power is 1, right? So y would be 1. You can choose any value you want for x. It doesn't matter. Anything in the real number system. When you take 1 and you raise it to a real number, you're going to get 1 back. So what ends up happening is you could basically say this is a horizontal line, right? It's the horizontal line, y equals 1. Or to make it match this format here, we could just say f of x is equal to 1, right? This is a horizontal line that would impact the y-axis at the point 0, 1. So there's kind of 2 things we're going to talk about in this lesson. The first thing is how to graph an exponential function. We'll spend a little bit of time on that. And then we'll move into solving exponential equations. So for graphing an exponential function, just a little bit of background here. The first thing you would do, just like if you were graphing anything else, you would find some ordered pairs, again, enough to show a good picture. You'd plot the points like you always do, and then you connect the points with a smooth curve. Again, I say this in a lot of videos, when you freehand draw things, if it's not a line, it's usually going to be pretty inaccurate, right? So you want to stick to just using this for a conceptual tool. If you actually need to graph something to look at it, you'd probably want to use either computer software or your graphing calculator. So let's start out with the graph of, you have f of x equals a to the power of x. So this kind of generic form that we could present it in our textbook. So the first thing is that 0, 1 is a point on the graph. Again, this is the x value. This is the y value. So in other words, if I plugged in a 0 for x, a to the power of 0 is going to give me 1, because any non-zero number raised to the power of 0 is going to give me 1. And remember, we restricted a to be greater than 0, and we also restricted a to not be equal to 1. So following those restrictions, we know if we plug in a 0 for x, we would get a 1 as a result for y. All right, so this is a very important feature when you deal with exponential functions. The graph approaches the x-axis, so it comes very, very close but it will never touch it. It forms something known as an asymptote, and we talked about those before when we were dealing with rational expressions. So now the domain, which is the set of allowable x values, consists of all real numbers. So again, because we restricted a, we could say that we can choose any value in the real number system from negative infinity to positive infinity as our input for x. Then the range, or the output, the values that we can use for y or for f of x, consist of all positive numbers. So 0 is not involved in that. And you can see the way that this interval notation is set up. Again, if you're using a parenthesis next to 0, it says 0 is not included, but anything larger is. So anything larger than 0, it could be 0.000000001. Okay, if it's larger than 0, it's acceptable, out to positive infinity. All right, so when a, your base, is greater than 1, the graph rises from left to right. So you're going to see it kind of over to the left. As you come from that direction and going to the right, you're going to see it just hockey stick itself up. And you'll see an example of this in a second. Then when a is greater than 0 and less than 1, the graph will fall from left to right. So in other words, it will start out at a higher point and it will decrease as it moves to the right. All right, so let's take a look at a few graphs now. So we want to graph each. And again, if we're doing this by hand, it's going to be just an approximation, right? We're just doing this to get a little practice on what it would look like. It's not going to be 100% accurate. So f of x is equal to 2 to the power of x. Let's choose about 5 values here, just enough to get a good picture. I'm going to choose some negative values. So I'm going to go with -4. I'm going to go with -1. I'm going to go with 0. I'm going to go with 1, and I'm going to go with 3. All right, so 0, 1 we know is a point on all of these. We talked about that a minute ago, so I can go ahead and just fill this out and say it's 0, 1. If I plugged in a 0 for x there, 2 to the power of 0 by rule is 1, so f of x or y would be 1. Now, if we look at the other ones, we say y instead of f of x is equal to 2 to the power of, in this case, x is -4. So if I plugged in a -4 for x, 2 to the power of -4 is what? This is 1 over 2 to the 4th power, which is 1 over 16. So we say this is 1/16 here. And then the next scenario is -1. So we know that if we had a -1 there, it would be 1 over 2 to the power of 1, which is just 1/2. So this guy would be 1/2. We've already figured this one out. That's 0, 1. So now we're dealing with positive exponents. So the first one would be 1. That's easy. 2 to the 1st power is just 2. And then the next one, if we raise this to the 3rd power or we cubed it, 2 cubed would be 8. All right, so our ordered pairs here, we know we'd have -4, 1/16. We know we'd have -1, 1/2. We know we'd have 0, 1. And we know we'd have 1, 2. And we know we'd have 3, 8. So let's copy these. Okay, so the first ordered pair is -4, 1/16. Now, the way this coordinate plane is drawn, the scale is in increments of 1. So obviously, I can't accurately portray 1/16. I just have to kind of guess at it. So if I go to -4 in the x-axis, that's here. 1/16, let's just say it's about right there. Okay, we're just showing a picture. Again, it doesn't have to be 100% accurate. Then the next point we're looking at is -1, 1/2. So -1 on the x-axis and then 1/2 on the y-axis. So that's about right there. Then we have 0, 1, so that's about right there. Then we have 1, 2, so that's about right there. And then we have 3, 8. So that's going to be 3 units to the right, 8 units up. That's about right there. And let me kind of go over these with a different color. All right, so as you go to the left here, as these numbers become bigger negative values, what happens is if we go back and you look at this guy, you have 2 to the power of something. If I have a really big negative, let's say it's 2 to the power of -10. Well, this is 1 over 2 to the 10th power. So as this number gets bigger and bigger, the denominator will get bigger and bigger. So the 1 is divided by a bigger and bigger number, so it becomes a smaller number overall. 2 to the 10th power is 1,024, so you can say I have 1 over 1,024. This is a small number, right? It's close to 0, but you can make this thing infinitely close to 0 as you choose bigger and bigger numbers in the negative realm for x. So if I chose negative 1 million, negative 1 billion, negative 2 trillion, something like that, you're getting the result for y, or the f of x value, very, very close to 0 because it's a very, very small number. It'll never be 0 and it'll never be negative. So that's why this guy right here, this asymptote gets formed, because it's going to approach 0, but it's never going to quite touch it. So it approaches the x-axis, a value where y would be 0, but it's never, ever going to actually get there. So the graph would look something like this. You kind of do like that, and then we just hockey stick itself up. We'll do that. Let's take a look at one more of these, and then we'll kind of look at some exponential equations. So we have f of x is equal to 1/2 raised to the power of x. So this guy here is between 0 and 1, so we would expect the graph to fall from left to right. So it's going to start out high, and then it's going to come low. It's going to approach the x-axis, but it's never going to touch it. So let's get some points going. Let's do -3. Let's do -1. Let's do 0. Let's do 1. And let's do 2. So I know that 0, 1 is a point on this graph. Again, I can always start with that because if I plugged in a 0 there, I know by rule I would get a 1, right? So f of x or y would be 1. Now let's think about the other ones. I have f of x, or probably be better just to put y, is equal to 1/2 raised to the power of -3. So how do I do this quickly? Again, I could flip the fraction here and make that exponent positive. So I could say this is equal to 2 over 1 raised to the power of 3. So 2 over 1 is just 2. 2 cubed is 8. So -3 is x, y is 8. Now, what if x was -1? What if x was -1? We would, again, flip the fraction, so it would become 2 over 1, and it would be raised to the first power. So that's just 2. 0, 1 we already have. If x was 1, y would just be 1/2. So then if x was 2, we could say this is 1 squared, which is 1, over 2 squared, which is 4, or simply 1/4. All right, so let's erase this, and we'll just kind of jot these ordered pairs down. So we have -3, 8. We have -1, 2. We have 0, 1. We have 1, 1/2. And we have 2, 1/4. So let's just copy this. So -3, 8. So -3, 8. It's going to be right there. -1, 2. So that's going to be right there. And 0, 1 is right there. 1, 1/2 will be about right there. And then 2, 1/4 would be about right there. So you can see this guy is going to fall from left to right. So in other words, it's going to come from up here, and it's going to fall as we move to the right. So we're going to go that way. We just say that it will, again, approach the x-axis, but it will never, ever, ever touch it. All right, so now that we've seen what an exponential function looks like, let's talk about solving exponential equations. And this is mostly what you're going to do in this section. So an exponential equation is just an equation where there's a variable and the exponent. So you see something like 2 to the power of x equals 16. Without me explaining how to actually conduct this operation, you could probably guess that x here is equal to 4, right? Just because you know that 2 to the 4th power is 16. But if you didn't know that off the top of your head, what would you do? So let's talk a little bit about this. So the first thing is just a little bit of a background. So I want you to recall from the last section that a horizontal line test is used to graphically determine if we have a one-to-one function. We've already looked at the graphs of two exponential functions. You can see that a horizontal line would not impact the graph in more than one location. It may seem a little confusing because of that area by the x-axis, but again, if you think about this, you're getting closer and closer to the x-axis. It's never the actual same value because it just keeps getting closer, infinitely closer, but it's never actually the same value. So a horizontal line would not impact the graph in more than one location. So we could say an exponential function is one-to-one. So because of that, we can use this kind of rule here. If a is raised to the power of x, and this is equal to a raised to the power of y, then we could say x is equal to y, given these restrictions here that a is greater than 0 and a does not equal 1. All right, so solving an exponential equation, each side must have the same base. And again, that goes back to this rule where we say if a to the power of x is equal to a to the power of y, the base here is the same. The base is the same. So we say simplify the exponents. That's the next step. We set the exponents equal to each other. We solve the resulting equation, and then we're going to check with substitution. So it's a very, very easy process overall. With the first one, we have 2 raised to the power of 3x minus 3. This is equal to 64. So the first thing you would do is think about, okay, 64 is 2 to what power, right? You want to express these as the same base. Well, you know it's 2 to the 6th power. So I would rewrite this and say this is 2 to the power of 3x minus 3 is equal to 2 to the 6th power. So now what do I have? I have the same base. Same base. So don't worry about the base. Just take the exponents. So this guy and this guy, simplify them and set them equal to each other. 3x minus 3 is already simplified. 6 is already simplified. So really all I have to do is say 3x minus 3 is equal to 6. I'm going to solve this very simple linear equation. So add 3 to each side of the equation. That's going to cancel. I'll have 3x is equal to 9. Divide both sides by 3. You get x is equal to 3. So the solution set here just contains the element 3. So let's erase all of this. So to check this, we're going to plug a 3 in for x right there. So you just think about this without even writing anything down. 3 times 3 is what? That would give you 9. Then if I subtracted away 3, that would give you 6. So you'd basically have 2 to the 6th power is equal to 64. Yeah, we know that's true, right? 2 to the 6th power is 64. You would end up with 64 equals 64. All right, so for the next one, we have 1/9 raised to the power of 3p is equal to 81. So this one's a little bit more challenging. We just want to think about how can I get 81 to have the same base as 1/9. So this is my base, and I want a base of 1/9. So what can I do? Well, just think about how you could get 1/9 and change it into 81 just using exponents. Well, I know that 9 squared would give me 81, but that's not going to quite do it because if I square 9 there, I'd have 1 over 81. So I've got to think about negative exponents. If I use a negative exponent, -2 would do the trick, right? So 1/9 raised to the power of -2, this would tell me to take the reciprocal of the fraction, 9 over 1, and square it, which would give me 81. So this is what I'm looking for here, a base of 1/9, an exponent of -2. So let's rewrite the problem to say it's 1/9 raised to the power of 3p, and this is equal to 1/9 raised to the power of -2. The exponents are simplified, so I could just set them equal to each other. So we'd say 3p is equal to -2. Divide both sides by 3. We'll say that p is equal to -2/3. So our solution set here will just contain -2/3. All right, what about 216 raised to the power of -3b minus 2 is equal to 36? So in this case, if I think about 36, I know that it's 6 squared. If I think about 216, I know that it's 6 cubed. So I want to just write this as 6 squared. I want to write this as 6 cubed. So I think about this just very carefully here. This 3 here would just multiply this. So I would have 6 raised to the power of 3 times, in parentheses, -3b minus 2. This would be equal to 6 squared. So if I simplify here, 3 times -3b is -9b. So let's write this over here. We'd have 6 raised to the power of -9b. And then 3 times -2 would be -6. And this equals 6 squared. So I have the same base now. All I need to do is take my exponents and set them equal to each other. So in other words, I will have the equation -9b minus 6 is equal to 2. I will add 6 to each side of the equation. That will give me -9b is equal to 8. Divide both sides of the equation by -9. This will give me b is equal to -8/9. So my solution set here will contain one element, just -8/9. All right, let's take a look at another one. So we have 64 raised to the power of 2 minus 2x times 16 raised to the power of -x minus 1, and this equals 1/4. So the first thing I'm going to do is I'm going to concentrate on simplifying this side. I know that 64 is 2 to the 6th power. I know that 16 is 2 to the 4th power. So let me write these with identical bases. Let's say this is 2 to the 6th power times this guy right here, 2 minus 2x, that quantity. Then times 16 is 2 to the 4th power times negative x minus 1, that quantity. And again, this equals 1/4. All right, so 6 times 2 is 12. So we would have 2 to the power of 12 minus 6 times 2x is 12x. And then times, we have 4 times negative x, that's negative 4x. 4 times negative 1 is minus 4. This equals 1/4. So now if we have the same base here, remember, if we're multiplying, we would add exponents. So I could add 12 and negative 4. That would give me 8. So this would be 2 to the power of 8. And then negative 12x minus 4x, that would be minus 16x. So 2 to the power of 8 minus 16x. And then if I have this equal to 1/4, let's think about how we could rewrite this to have a base of 2. Well, I could say that 4 is 2 squared. So that's easy enough, but I need 2 to be in the denominator, not the numerator. So I could really rewrite this and say this is 2 raised to the power of negative 2, right? Because this is 1 over 2 squared, which is 1/4. So let's write this as 2 raised to the power of negative 2. And now I'm good to go. I know it seems like a lot of work, seems kind of tedious, but really if you know the steps, if you know your rules for exponents, it's not too bad. All right, so 2 and 2, same base. Just going to set these guys equal to each other. I'll say 8 minus 16x is equal to negative 2, and I'll just solve for x. So I'm going to subtract 8 away from each side of the equation. That'll cancel. We'll have negative 16x is equal to negative 10. We'll divide both sides of the equation by negative 16. And so that's going to cancel with that. We'll have x is equal to positive. If you think about 10, it's divisible by 2. Divided by 2, you get 5. Divide 16 by 2, you get 8. So x equals 5/8. So again, x equals 5/8. All right, so the next problem is 64 raised to the power of 3p plus 3 times 1/8 raised to the power of 2p. This equals 64 raised to the power of negative p minus 3. Now, we have a 64, a 1/8, and a 64. So let me just use a base of 8. That would be easy. So in other words, I will take 64 and say this is 8 squared. And this is multiplied by the quantity 3p plus 3 up here when we talk about the exponents. Then times, for 1/8, I could really write that as 8 to the power of negative 1, and that's times 2p. And this equals, for 64, again, I could write that as 8 squared, and the 2 will be multiplied by the quantity negative p minus 3. So we'll have 8, and then 2 times 3p is 6p, plus 2 times 3 is 6, and then times 8 raised to the power of negative 1 times 2p is negative 2p, and this equals 8 raised to the power of 2 times negative p is negative 2p, and then 2 times negative 3 is negative 6, or minus 6. Now, we have 8 raised to the power of 6p plus 6 times 8 raised to the power of negative 2p. If you're multiplying here with the same base, you add the exponents. So, in other words, I would just add 6p and negative 2p to give me 4p. So this would be 8 raised to the power of 4p plus 6 is equal to 8 raised to the power of negative 2p minus 6. So now we have the same base, so we can just look at the exponents. So we'd have 4p plus 6 is equal to negative 2p minus 6. We can subtract 6 away from each side of the equation. That's gone. We can add 2p to each side of the equation. That's gone. So I'll have 6p is equal to negative 6 minus 6 is negative 12. Divide both sides of the equation by 6. We get that p equals negative 2. All right, let's erase everything. So again, p equals negative 2.